Hi folks, this video is on the quotient law of logarithms. So we're going to take it back to exponents for a little while, just as a quick refresher. And as you can see on the left-hand side here, we have a quotient of two exponential numbers. Their bases are the same. So when we have that happening, we can subtract their exponents. So x to the power a over x to the power b equals x to the power a minus b. We can show that with some numbers here. So x power 10 divided by x power 3 ends up being x power 10 minus 3, which is 7. Feel free to pause it and give this a try on your own. X to the power 8 divided by x power negative 5 is x to the power 8 minus a negative 5, which ends up being x to the power 13. Similarly, we have a quotient law for logarithms. Here's our quotient. This was the quotient in the exponent example. And in the exponent example, we had a quotient and then we had some subtraction. In the logarithmic example, we have a quotient and we have some subtraction. So two ways to think about the quotient law. First way is when we have a logarithm acting on an argument that is a quotient, we can separate that into two different logarithms. So it can be the logarithm of the numerator, subtract the logarithm of the denominator. The other way to think about this is to go the other way, where we have two separate logarithms, and if they have the same base and they're subtracting each other, then we can turn that into a single logarithm, where the argument of the logarithm that is being added, or that's positive, goes in the numerator, and the argument that's negative, or being subtracted, goes into the denominator. So let's just run through a couple of examples. Log base 2 of 18 minus log base 2 of 6 ends up being log base 2 of 18 over 6. Now we can actually simplify this to get log base 2, and then 18 divided by 6 is just 3. So log base 2 of 3 is the simplest form of this one. The one below, we have log base x of 28 minus log base x of 7. So again, we have two logarithms separated by subtraction, so we can combine that into one, which gives us log base x of 28 over 7. And again, we can simplify our argument. So log base x of 4. This brings us to the proof of the quotient law. You may be asked to prove this. So our quotient law is over here on the right-hand side. And we're going to start with a couple of things here and get it to look like our law. So first thing we can do is we can write both of these in exponential form. So with that a over to the other side, so m equals a to the power x. And we do the same thing with our second one. So n equals a to the power y. Now it's the quotient law, so we need a quotient. We have m over n here. So let's start with an m over n. Now m is equal to a to the power x, and n is a to the power y. So m over n equals a to the power x over a to the power y. We're just working with our exponent law, which says when we're dividing our exponential numbers, we get to subtract their exponents. So m over n is equal to a to the power x minus y. Now I have an exponential expression over here on the right. So I'm going to put this into logarithmic form. So I'm going to move the a to the other side. So we have log base a, and then my argument is going to be m over n equals x minus y. Now I'm going to continue my work over on the side here just so we don't lose what we can see here. So log base a of m over n equals, now x, by very definition at the very start, we said that's equal to log base a of m. So log base a of m, and then we're going to subtract y. And again, our definition at the very start here says log base a of n. And this here is exactly what our law is. Now let's work through a couple of applications. So we want to write these as single logarithms. Feel free to pause these and do them yourself before I get to them. We have two logarithms with the same base being subtracted, so I can turn this into 1 log base 7 of 221 over 18. If you can simplify the argument, you can, but it's not necessary at this point in time. Our next example, again, we have logarithms with common bases, and one is subtracting the other. So we have log base b of x over y. Getting a little bit more difficult now, where we're going to do some solving. So before we had two logarithms, we made it 1. Now we have 1, and we're going to turn that into 2. So when we have a quotient, that means we can separate these arguments as different logarithms with subtraction. So we get log base 3 of 27 minus log base 3 of 81. Remember, the denominator is the one that ends up being subtracted. So at this point in time, I'm going to make two substitutions. I'm going to say x is equal to log base 3 of 27. And then I'm going to say that y is equal to log base 3 of 81. So to substitute these, I'm going to put them into exponential form. So 3 to the power x equals 27. Now I want to express 27 with a base of 3. So 3 to the power x equals 3 to the power 3. And through that, I know that x is equal to 3. We're going to do the same thing with y over here. So put it into exponential form, 3 to the power y equals 81. Then we want to express 81 as 3 to the power something. So 3 to the power y is equal to 3 to the power 4, which is 81. Then the bases are the same, so the exponents must be the same. So y is equal to 4. So remember that this was x, and our other one was y, so we have x minus y. So we really just have x value of 3 minus y value of 4. So our final answer is negative 1. Let's move back to our other one here. Same idea. We're going to separate it into two logarithms. So log base 2 of 64 minus log base 2 of 0.5. I'm going to try to do this work over on the side now. So I'm going to say x is equal to log base 2 of 64. So we're going to put this in exponential form, 2 to the power x equals 64. And I want to express 64 as 2 to the power something. 64 is 2 to the power 6. Our bases are the same, so now x is equal to 6. So log base 2 of 64 is equal to x. I'm going to let log base 2 of 0.5 equal y. So y equals log base 2 of 0.5. I move the base to the other side, put it into exponential form. And I'm not a huge fan of decimals. You probably know that about me by now. So I'm going to express this as 1 over 2. Now I understand that some of you don't love fractions. So what we can do is we could actually write this without the fraction, and this is going to be 2 to the power negative 1. So if that's the case, if 2 to the power y is equal to 2 to the power negative 1, the bases are the same, so the exponents must be the same. So my y value is negative 1. X we said was 6. Subtract. This is a negative 1. So when you subtract a negative, it's like you're adding it. So our answer is 7. One last example. Given log x of y equals 3a and log base x of z equals 2a, solve log base x of y over z. So log base x of y over z. I have log base x of y, and I have log base x of z, but not with them together. So let's expand this to be two separate logarithms. Log base x of y minus log base x of z. And now I can just do substitution. Log base x of y is 3a, so this is 3a. Log base x of z is 2a, So 3a minus 2a is just a.